Assalamualaikum warahmatullahi wabarakatuh and greetings everyone. My name is Jessica Fathin Humairah, 136181118. And in this video, I will present to you the mission reconstruction I have done for the third assignment of the astronautics course. And the mission I have chosen is the Akatsuki. The Akatsuki, also known as the Venus Climate Orbiter, is a space probe launched by JAXA or Japan Aerospace Exploration Agency to orbit the planet of Venus to study its atmosphere. The Akatsuki was launched aboard an H2A202 launch vehicle on May 20, 2010 at Tanegashima Space Center. The spacecraft failed to conduct the orbital insertion maneuver to the Venus orbit on December 6, 2010. After the spacecraft orbited the Sun for approximately 5 years, the spacecraft was finally able to go into Venus's orbit. The spacecraft has launch mass of 517.6 kilograms, dry mass of 320 kilograms. The dimensions as shown in the table. The power greater than 700 watts at 0.7 astronomical units. The propellant used is the bipropellant hydrazine dinitrogen tetroxide with specific impulse of 335 seconds. As mentioned earlier, the launch vehicle used is the H2A202 rocket. The 202 has two solid rocket boosters, one first stage and one second stage, and no liquid rocket boosters and no solid strap-on boosters. The propellant mass and the specific impulse and the necessary parameters are shown in the tables. And from here, this is the launch capability of the launch vehicle. If we look at the figure, we know that the maximum altitude that can be reached by the rocket is 828 kilometers above the Earth's surface. So from here, this altitude will be used as the parking orbit altitude. The launch site of the Akatsuki mission is the Tanegashima Space Center, which is located at the south of Kagoshima Prefecture. It is the largest rocket launch complex in Japan with a total area of about 9,700,000 square meters. The latitude, and the longitude are shown in the table, and the operator of this launch site is, of course, the Japan Aerospace Exploration Agency. So this figure shows the trajectory of Akatsuki from the Earth to the Venus orbit. And if we see this figure, we know that the distance of Earth to the Sun is farther than the Venus to the Sun. So therefore, the assumptions used are the spacecraft is not affected by any celestial bodies except the Earth, Sun, and Venus. The orbits of Earth and Venus around the Sun are on the same plane or zero inclination. The parking orbits of the spacecraft on Earth and Venus are circular. The rocket used or the propellant used is impulsive, meaning that there will be no time spent for the changing velocities for the special maneuvers. So the process happens instantaneously. And then at the start of the transfer orbit, the Earth is located at its aphelion, meaning that it is located furthest away from the Sun. At the end of the transfer orbit, Venus is located at its perihelion, meaning that the Venus is located closest to the Sun. And then no failure occurs in the satellite during mission. The failures include, if there are any, trajectory correction maneuvers, and of course include the failure of Venus orbit insertion. So here are the orbital parameters. For the Earth and Venus, we need the mean distances to the Sun, the aphelions, the perihelions, the mean radii, the gravitational parameters, and the sphere of influence radii. As for the Sun, since it is located at the center of the solar system, we will only need the gravitational parameter. The mission reconstruction are divided into several phases. So the first one is the launch phase, although not necessary for the trajectory calculations. So the first launch is the solid rocket booster A launching. And the Tsiolkovsky equation is used to determine the speed increment, as the equation is shown on the right, and the speed increment for the solid rocket booster launching is 1.655 kilometer per second. Then goes the first stage launching, in which we will use the initial mass of that has already been subtracted by the fuel, by the propellant due to solid rocket booster A launching. The speed increment used is 4.336 kilometer per second. Next is the parking orbit phase. From the figure we have discussed earlier, we know that the parking altitude is equal to 828 kilometers above the Earth's surface. From here, we can calculate the parking orbit velocity using the Fish-Viva integral, in which the velocity is equal to 7.441 kilometer per second. And then, in order for the spacecraft to be able to reach Venus, it has to go to heliocentric transfer orbit. However, to go to that heliocentric transfer orbit, we have to determine the hyperbolic escape trajectory first. The hyperbolic escape trajectory from this figure is shown in the curve colored in red, whereas the parking orbit is shown in curve colored in blue. And then we have to calculate several velocities and some parameters. The first one is the velocity of Earth with respect to the Sun, which is equal to 29.783 kilometer per second. And then we have to calculate the spacecraft velocity at aphelion, which is equal to 27.287. However, before calculating that velocity, we have to calculate the semi-major axis, which is equal to 128.9 times 10 to the power of 6 kilometers. Then we have to calculate the hyperbolic excess velocity, or the V infinity, which is equal to minus 2.496 kilometer per second. Then we can calculate the characteristic energy, which is simply by squaring the V infinity, which is equal to 6.23 kilometer square per second square. Next, we have to calculate the spacecraft hyperbolic perigee velocity. But before that, we have to calculate the hyperbolic semi-major axis. in which we get the minus semi-major axis equal to 63,980.574 kilometer. And the spacecraft hyperbolic perigee velocity can be calculated, which is equal to 10.223 kilometer per second. And finally, we are able to obtain the speed difference or delta V by subtracting the spacecraft hyperbolic perigee velocity by the parking orbit velocity, which is equal to 2.782 kilometer per second. After obtaining the delta V, we use again the Tsiolkovsky equation. And for this particular mass of required propellant, we use the second stage of the launch vehicle, in which we have the specific impulse equal to 448 seconds. From here, we get that the fuel or the mass of required propellant is equal to 9,531.6171 kilograms. And then we are able to determine the heliocentric transfer orbit. However, first we need to calculate the radius of parking orbit at Venus. From the reference, we get that the pericenter radius is equal to 400 plus the radius of the Venus, and then the apocenter radius is equal to 440,000 kilometers. Then we get that the parking orbit radius at Venus is equal to 223,225.9 kilometers. After obtaining the parking orbit radius at the Venus, we can calculate the aphelion and perihelion of the heliocentric transfer orbit by taking into account the parking orbit radiuses. The aphelion of the heliocentric transfer orbit is equal to 152 million and 107,199 kilometers. And then the perihelion is equal to 107,723,225.9 kilometers. From here, we get the semi-major axis, which is equal to 129,915,212.5 kilometers. After obtaining the semi-major axis, we can calculate the orbital period using this equation, in which we will get the orbital period of 25,540,795.45 seconds. However, the trajectory used will only take half of the orbit, so we divide the orbital period by 2, so we will get the time for Akatsuki to reach Venus orbit, that is equal to 12,778,397.73 seconds, which is approximately equal to 148 days. When the spacecraft approaches Venus, the spacecraft needs to go to hyperbolic arrival trajectory, as shown in this figure. The hyperbolic arrival trajectory is shown by the curve colored in red, whereas the parking orbit radius or trajectory is shown by the curve colored in blue, which is also named as capture orbit in the figure. Same as the hyperbolic escape trajectory, we also need to calculate the velocity, several velocities. First, we have to calculate the velocity of Venus with respect to the Sun, which is equal to 35.020 kilometer per second. And then we have to calculate the spacecraft velocity at perihelion, which is equal to 37.728 kilometer per second. Next, we can determine the V infinity, which is equal to minus 2.708 kilometer per second, and the characteristic energy, which is V infinite square, equal to 7.333 kilometers square per second square. And then to calculate the spacecraft hyperbolic perigee velocity, we have to calculate the hyperbolic semi-major axis and the hyperbolic eccentricity, and in which we will get the semi-major axis and the eccentricity as shown in this slide. The spacecraft hyperbolic perigee velocity is equal to minus 3.2 kilometer per second. And then, as we have already obtained the parking orbit radius, we can calculate the parking orbit velocity, which is equal to 1.206 kilometer per second. And then we can obtain the delta V, which is equal to 1.994 kilometer per second. And now we can calculate the mass of required propellant. In here, we are now using the propellant of the spacecraft, which has the specific impulse of 335 seconds. And then, by using the Tsiolkovsky equation once more, we obtain the fuel mass equal to 235.256 kilometer per second. And now we are going to analyze the data obtained through analytical means and the reference data. However, we only have two parameters to be compared since there is no sufficient data available on the internet for the other parameters such as characteristic energy or the delta V at each maneuvers. So the first parameter is the time to Venus if real mission succeeded its Venus orbital insertion on first attempt. So we get that the analytical is equal to 148 days, whereas the real data is equal to 200 days. We obtain the 200 days by counting the days from May 20 to December 6. And the error we get from here is 35.14%. And then the next parameter is the propellant mass for the Venus orbit insertion. We get that the analytical propellant mass obtained is 235.256 kilograms, whereas the reference data, although not explicitly stated, we calculate the launch mass and then subtract it by dry mass to get the propellant mass, which is equal to 197.6 kilogram. This yields an error equal to 16%. So we get these errors because of the assumptions we use. And of the assumptions we use, especially for the sixth one, in which we do not take into account any failure that occurs during the satellite mission. Also, for the propellant mass, the analytical result is calculated by considering the specific impulse and the gravity for the Tsiolkovsky equation of that of Earth's, not that of the Venus's. If we, this is because we have only tested the propellant at Earth, not at Venus. So we get this error, which is quite high, although not as high as the error of time to Venus. Okay, so that concludes the video. Thank you for watching, and I hope you all find this video useful. Thank you very much.